research effort to do what the title said, the high-dimensional combinatorics. And it turns out almost everything that we do in standard combinatorics has very interesting higher dimensional counterparts. And it's very interesting to understand these things and study their properties and so on. And you often hear the statement, if you listen to the right people, that a graph is a one-dimensional simplicial complex. So the first thing that I want to do is to make sure that we all know what simplicial complexes are and do some of the basic definitions and concepts that are related to them. And then what I want to do next, and I mean, if we have time, I'll perhaps do more, but I think it's a fair assumption that I will try to describe to you a series of studies, papers that we've done, which the idea is let's take the most basic model of random graphs, which is Gnp, and see how the analogous questions, how to develop an analogous result in higher dimension. And as it turns out, there are really very interesting and fascinating things. We already know quite a few things, but there are many more mysteries that we haven't explored yet. And so that's the plan of my lecture. So I want to start with what is a simplicial complex. So for a combinatorialist, the simplicial complex is really a very natural object. So you start with a set of vertices. Everything is going to be finite. This is a finite set, and unless I say otherwise, this is a set of cardinality n. And X is a collection of subsets of V, which is closed down. And that means if A is in this collection, and B is a subset of A, then you can conclude that B is in X as well. Now, the members of X are called faces. Such an A is called a face or a simplex. And we associate a dimension. So again, very simple and very natural. The dimension of a set A or a face A is simply defined as the cardinality of A minus 1. Think about it. If it's a vertex, we want to think of it as being zero-dimensional. An edge, two vertices is one-dimensional, and so on and so forth. And the dimension of the simplicial complex is just the highest dimension. The highest dimension of a face in X. Okay, so one thing to see is that now we can really understand this statement. This statement is now becoming completely obvious. A graph has two types of faces, zero-dimensional, which we normally call vertices, or we call them vertices here as well, and one-dimensional, which we call edges. And that's it. The being closed down is completely trivial, and so there is really no problem. Okay, so you can study many different things about simplicial complexes, and the general plan is that let's try to take whatever we already know, or perhaps I should say one more word, which I'm not going to develop too much, but just why are geometers or topologists, or why were they at least interested in these creatures? Because they provide you with a very good means of describing geometric objects, possibly quite complicated ones. So for example, you can see, just as an illustration, this is a simplicial complex with 6 vertices. It has this two-dimensional face 1, 2, 6. Now, I don't even say, but from the definition, it follows that the face, the one-dimensional face 1, 6 is there too. And this two-dimensional face, there is no, this 2, 3, 5 is not a face. So by gluing together simplices, and that also explains to you why we call them, with the appropriate dimensions, you can really construct complicated geometric objects, and that gives you a way of dealing with them, of handling them, and understanding them. So So one of the nice things about this concept is it's really a very natural spot where combinatorics and geometry meet. So the main plan, that the things that I want to tell you about is I would like to speak about the concept of random simplicial complexes. And I'm going to do everything in light of what we know in the one-dimensional case. So this whole research program works in this way. Let's take stuff that we know about graphs in the one dimension, and let's ask ourselves, is there a similar phenomenon, or are the phenomena changing? What are the analogous questions in higher dimension? So the simplest model of random graphs in D equals 1 in graphs, the simplest model of random graphs is the Erdős-Renyi GNP model. So what is this? You start with n vertices. There are two parameters. N is an integer, p is a number between 0 and 1. You start with n vertices. And for every pair of vertices with probability p and in an independent fashion, you put an edge with probability 1 minus p, there is no edge. And there are many wonderful phenomena related to this, and I want to do everything in light of this very basic theory. That's the general plan. Now, let me just say very briefly that the most important meta-discovery that Erdős and Renyi did, which we actually only understood in full much later, so an important contributor to this perspective is Ehud Friedgut, who sits here, is the phenomenon of threshold. So without going too much into this, which is a wonderful subject in its own right.
I never see my blind spot so clearly.
Point to someone and then the camera finds.
Okay, Gataish, right. So what are thresholds? So I'll illustrate this with one very specific example, which I want to speak about in greater detail anyway, connectivity. So here I said GNP, and I didn't even refer to what this P is, but in most interesting cases, and in fact in every case that we will be dealing with today, P is allowed to depend on N, and all the phenomena, the interesting phenomena that we will be talking about today are of this form. So the question is about connectivity. So let's think about it for a moment. So P is running from 0 to 1. And here I want to write what is the probability that G that we draw from GNP, a random graph like this, if we generate a graph in the form that I described before, what's the probability that this graph is connected? Now, even if you don't have much background in this, it should be obvious to you. This is a monotone property. So the larger the P, the more dense the graph is, and the more likely it is to be connected. But the important discovery, which, as I said, we really understood in full only later, but in this specific case, for example, already Erdős and Renyi knew that this graph looks something like this. So it's really, so there is a very short interval. I'm glossing over many things here. I just want to give the main point that over a very short interval, the probability jumps from 0 to 1. And so there are many interesting things that one might ask, but perhaps the first question is, you want to know where this happens. And this happens, this is a result that Erdős and Renyi proved, that the critical P here is log n, which is actually ln n over n. And there is one part of this which is really easy. It's very easy to see that if P is, let's say, 1 minus epsilon times ln n over n, then G is almost surely disconnected. Actually, not only is it disconnected, actually, almost surely has isolated vertices. And this is really just a coupon collector, very simple coupon collector argument. What takes a little bit more work, and certainly was, a major discovery when they did this, but today it's a fairly easy thing to prove, is that this is completely easy, and what you want to show is that if P is a little larger, this part of then almost surely G is connected. Okay, so let's try to understand how do we even, so this is a very basic fact, which we now know this is late 50s, early 60s, it's really many, many years. And we are seeking a high-dimensional analog. So the first question is how do we want to pose the question? What is the analog of this model, and so on and so forth. There are many things which are not obvious that you want to start with. So you also in graph theory incidence matrices. The incidence matrix of a graph G is a matrix where the rows correspond to the vertices, the columns correspond to edges, and if this is the edge ij, then let's say there is a +1 in the ith row and a -1 in the jth row. Doesn't matter which way. It doesn't. We need them to be plus or -1. Or if you want to work, this is if you want to work over the reals or over the complex, over the rationals. If you want to work over F2, the field with two elements, which we often, if nothing else, for purposes of simplicity, then it's a matrix like this. And this encodes, of course, the full information about the graph. And as we shall see, that's a good place to start. And the reason is that this matrix is really an object that plays an important role in topology when you take it to a higher dimension. And yes, please.
On the right hand side you have +1, +1, on the left hand side +1, -1. What do the ones and -1s represent?
Okay, good question. So what does such a matrix? Let's start with this. This is the more usual way that people look at this. So these are the edges of the graph. The columns correspond to the edges of the graph, and if this is the edge ij, then in this column there is a 1 in the ith row, a 1 in the jth row, and everything else is zeros. Okay? There's also a version which you can think of as the directed graph, which looks like this. And as we will see, sometimes the underlying field is of interest and makes things, changes things. The simplest description is usually over F2, where there is no minus, the -1 is a plus. So depending on the case, we will either be working with this or with that. Okay? But this is really a special case of something general that people use when they're looking at simplicial complexes. And this is a matrix which, this matrix as a linear operator is the so-called boundary operator. So you see here, think of it, this is the dimension 0 part of the complex versus the dimension 1 part of the complex. And this matrix tells you how the two things relate to each other. In general, you can take, if you have a general simplicial complex X, you can look at matrices, at a matrix where these are the faces of dimension x d minus 1, the faces of dimension d minus 1 in x, and versus the faces of dimension d of x. And here you can, again, very similarly, you can do the same thing. If you're working over the field with two elements, then here, this is, let's illustrate it for d equals 2. So if this is the face ijk, then there will be, the rows are marked by pairs because that's a two-dimensional. So there is a row for ij, row for ik, and row for jk. There will be a +1 here, a +1 here, and a +1 here, and zeros elsewhere. Okay, so this matrix is the, let's say, the two-dimensional, in general, d-dimensional. So this is just, so over F2, you have the inclusion matrix of d minus 1 versus d dimensional faces in X. Now, if you work over fields of characteristics 0, then, or other fields, not F2, then there is also an issue of signs here, which corresponds to orientation. So I don't want to go into this. This is a bit technical and not so crucial for what we want to do today, but I just want to illustrate the simplest case, which can be easily drawn on in the plane. So what do? Every edge, I'm describing to you the issue of signs in 2 dimensions. So these are going to be one-dimensional faces. These are going to be, so edges, these are going to be 2-dimensional. When I work in 2 dimensions, I'll just refer to everything as vertices, edges, and faces. They're only going to be 2-dimensional, so I don't need to have more vocabulary than that. So you start with an arbitrary orientation of the edges. Doesn't matter. You pick one and fix it once and for all. And then you also orient the faces. So it's very clear what it means that I want to orient a 2-dimensional face. I can go either clockwise or counterclockwise. And now in the corresponding matrix, first of all, the non-zero entries that correspond to this in the column that corresponds to this face are going to be in the rows that correspond to these guys. And they're going to be +1 and -1 according to whether this orientation and this orientation are consistent. For example, you see, the face is inconsistently oriented with this because the face here goes this way. It's consistently oriented with that and consistently oriented with that. Correspondingly, there will be a -1 here, a 1 here, and a 1 here. But really don't worry about this. If this orientation business confuses you, it's not going to be too crucial for us. So there is one fundamental fact that you need to know, which is really easy. I will not prove it to you, but if you think about it for 2 minutes, you'll verify it very easily. So this is what I wrote here. This is the d-dimensional boundary operator. And if you multiply 2 such matrices, one by the other, next to the consecutive ones, if you multiply this matrix by this, so this is a matrix and this is a matrix, it's very easy to check that you get the zero matrix. Okay? So these are very fundamental facts. Let's just think about just very, very simply here in graphs. There's really not much that we can do here, but we can go down. What is the zero, order 0 here? So that will be just one vector of all ones. There is only one minus one-dimensional face, the empty set, and all the 0-dimensional faces, which are the vertices, and it's the all one vector. What does this? How does this translate? If you take the all one vector and you multiply it on the left by this matrix, you actually get the zero vector. This will be useful for us. Okay. So remember, we're talking about the Erdős and Renyi threshold for connectivity, and now the main point in the discussion that I'm carrying out now is that it's really a good idea to think about connectivity. Of course, there are many, we saw Menger before, and so there's a lot of very basic graph theory dealing with connectivity. But actually, in speaking about these things in linear algebra terms, in these matrices, is really very, very. So here is an observation. A very simple observation, but quite a useful one. A graph G. So let's give it a name. Let's say for a graph, let's call it AG. So remember, the O1 vector times AG is 0. That's a simple observation that we had before, which if we wanted, we could consider as a special case of this. A graph G is connected if and only if the only solution up to normalization to xa equals 0 is x equals the all ones vector. Of course, you can multiply it by in other words, connectivity means is the same thing as no non-trivial left kernel. So why? Let's just think about it for a moment. Why is this observation correct? If the graph is disconnected, then if you take instead of the all ones vector, the characteristic vector, the indicator vector of a connected component, you also get 0. But that's an if and only if. That's the only way you're going to get a non-trivial left kernel. And this is what I want to take as my definition. Of course, there is nothing new here, and at least there are a few people here who know this much better than I do. For topologists, this just means the zeroth homology, is it 0 or not? That's the condition. But I don't want to try to explain these things. There are people here, as I said, who can explain this much better than I, so I will not even try. Okay, good. So this really provides you with the means of at least speaking about a notion of connectivity. Let's do in most, I mean, I think nothing that I do today is really limited to 2 dimensions, but you'll usually see the whole picture when we just move from 1 to 2 dimensions. So to illustrate things, I will mostly speak about that, although everything that I think almost everything that I'll tell today works just as well for general dimension. So you could ask, so now let's go to 2 dimensions. I have here the 1-dimensional faces, the edges. I have some simplicial complex, 2-dimensional. I have here the edges, and I have here the faces. And I have, let's say, something like this, a matrix like this. Everything else is zeros. And I want to translate into concrete terms this notion. What does it mean that this matrix has no non-trivial left kernel? So the thing to think about is that non-trivial for graphs was just what's the trivial part? That's the trivial part. But here I know that if I multiply this by this, I get a 0. So this means when I see something like this, that's a matrix with which I'm dealing now. So this means that the row space of this is, of course, included in the left kernel of this. So what I should consider as a trivial object in the left kernel is anything that's spanned by the rows of this matrix. And so what is the trivial left kernel? It's the rows of this matrix. These are the vertices. These are all the pairs. So every such a thing is trivially in the left kernel of this. Okay, so now let me set the ground. So at least I understand what question am I asking. And now let me set the ground precisely to what I want to do. And so first I need a definition, something like GNP. And this is something that Roy Meshulam and I did about 10 or 12 years ago. And so this is the A higher dimensional analog Yes, please.
What typically would be the rank of this row space? Would it be everything but one?
Okay, so I will come to this in a minute. I don't want to jump ahead of myself, but I'll answer the question in just a minute. So a high-dimensional analog of Gnp. So what we do, d-dimensional. So here is a complex. So remember, we had the vertices, and then we throw in edges independently with probability p. We do something very similar. We take a full d-1 dimensional skeleton, which means, i.e., every face of dimension less than or equal to d-1 is there. And then we introduce d-dimensional faces independently with probability p. That's the model. That's the model that with Roy Meshulam we introduced. And now I can ask this question in a precise manner. So let me come back again and restate what Erdős and Rényi did, and then at least we're able to ask a very concrete and accurate question and actually give it an answer. So here's I want to restate the Erdős and Rényi result from the perspective that we have right now. You start with the incidence matrix of the complete graph, n by n choose 2. And what you do now, that's rather than having this description, that's the description that I want. I pick every column independently with probability p. With probability p, I maintain it. With probability 1 minus p, I throw it away. So on average, I just write here, of course, that's just an average, but just to remind ourselves what we're doing. We're talking about a matrix that roughly looks like n by p times n choose 2, where these columns were selected. And the question that Erdős and Rényi asked is, what is the critical p for the property no non-trivial left kernel? And remember, the answer to this question is ln n, p equals ln n over n. But using this formulation, now I'm completely set up to ask a completely concrete question. So I do precisely the analogous thing. I start with a matrix of n choose 2, all the pairs by n choose 3, where again, if this is, every column has 3 non-zeros, which are plus or minus, everything else is 0. Now I pick every column independently with probability p, and with probability 1 minus p, I throw it away. I do it independently for each column, and I ask the same question. What is the critical p for which this matrix has no non-trivial left kernel? So let's say, yes, Ron. Yeah, no, please.
These signs, earlier you said that they're somewhat arbitrary. You orient some faces this way and some faces that way.
It really doesn't matter. So think, no. It's completely obvious, because if I selected to switch, let's say, the orientation on this edge, this means I multiply this row by -1. If I selected to the column, I multiply this column by -1. So in terms of these are elementary operations, they don't change anything. Okay. So now we really want to dig a little deeper into what the trivial part is. So we said it's the row space of the previous matrix. So what does such a row typically look like? It's vertex number I. And here are all the edges. What are the plus and minus terms here? The non-zero terms. They exactly correspond to all the edges ij. In other words, this is the indicator vector of the star centered at I. Okay? And what do I get when I add such things? In general, the space of the left kernel, which is a linear space, consists of the indicator vectors, all indicator vectors of all complete bipartite graphs. I partition the vertices into two parts, and these are the obvious or the trivial members of the left kernel. And the question is, when is it? So of course, even if I take everything, if I take and choose three columns, then these will be in the left kernel. And of course, the more columns that with fewer columns, there will be more things in the left kernel, and the more columns that I add, they become smaller and smaller. The question is, when have we gotten rid of everything but the things that will remain there forever? Now let us remind ourselves what the answer was. At least we were able now to, in light of Erdős and Reddy's work, we're able to come up with a reasonable guess. The answer there coincided, quite surprisingly, I suppose, if you see this for the first time, with the answer to, so that's not how the proof works, but I just analyze what the answer was. So in Erdős-Renyi, the P critical for connectivity, or P connectivity, the critical P for connectivity, coincides with the P for no isolated vertices. That's the proof gave it to us. It wasn't clear a priori. There is an obvious inequality between the two, but they actually coincide. What does an isolated vertex look like in terms of these matrices? An isolated vertex, if these are vertices versus edges, means that this row is all zeros. It belongs to no edge. And of course, if there is such a row, then you have a non-trivial left kernel, just pick up, the EI that corresponds to this. So this is suggestive that perhaps something similar happens here. So again, if we pick so few rows, so few columns, that one row is completely zero, then of course there is a non-trivial left kernel. So doing this calculation is again a coupon collector argument. And a simple coupon collector argument, the same thing, by simple coupon collector argument, it is very easy to see that if P is less than 2 times ln n over n, then there exists a zero row. What does a zero row mean when we're talking about two-dimensional simplicial complexes? That's an edge that is not covered by any face. And this, of course, means that in this case, there is a non-trivial left kernel. What is this 2 ln n? It's just the ln of n choose 2. That's all. That's all there is.
Maybe it is done by the rows, but all the rows sum up to 0.
No. We're talking about left kernel.
Okay, whether it is done by the rows.
No, I'm talking about left kernel. Can you multiply by anything from the left that will give you 0, where this vector is non-trivial? You didn't say that it's non-trivial. Yeah. Why? That's a very easy thing to check. Okay, yeah, good question, but it's a very easy. I will not do the details, but it's very easy to check. So this suggests a possible answer to this, and this is in fact the theorem. So in work that Meshulam and I did, and later Meshulam and his PhD student Wallach did, the following theorem was proved. So this is, I'm combining here my work with Meshulam and his work with the critical P for the vanishing of HD minus 1. I'm still not revealing everything here, so bear with me for a moment and I'll try to do everything in full, i.e. no non-trivial left kernel to the boundary operator matrix is P d ln n over n. So let me just say that the argument that we said before, that if P is, let's say, less than 1 minus epsilon times that, that's really easy for the same reason that we had before. And the work goes, and I'll try to give you at least one item from the proof that the main thing that one has to prove is that if this is, so what does this say? That here there exists a non-trivial left kernel. And here we want to say that there is no non-trivial left kernel. Okay, so D, sorry. Yeah, okay. There too, right. You're absolutely right. Thank you. Okay.
Is it like the graph case? Does it hold in strong sense?
Yeah, I think this was done later on. You mean the stopping time? Yeah. Okay. So let me now be a bit. So of course, all these things may depend on the field over which you're working, and there are also versions for so which coefficient rings. And I will only say that we know this only for any finite abelian group of coefficients. It's also interesting to understand what happens when the coefficient ring is Z. And then this has been looked into. There are very nice there is very nice work on this, but I don't want to. But there we still don't have the final answer. Okay, so I want to give you at least one taste of a nice point that can be explained on the board from that proof. And this, at least I hope, will also help Tali when she speaks, Tali Kaufman. I think it may be relevant to, to what extent we can rely on each other's lectures, I don't know, but at least we can tell it to ourselves that it is useful, so why not? Okay, so I will do everything just in the two-dimensional case, and let's think about it for a moment. So we have, for short, I will look at this matrix. So understand what this is. I start with a full n choose 2 by n choose 3 matrix. I pick columns independently with probability p. And now I would like to know, I would like to be able to claim something like this, that if p is sufficiently large, if I picked up enough columns here independently, then the only things in the left kernel are the obvious suspects, which are, let me remind you, are these guys. Okay, but I want to even make let me again, just to simplify matters, let's do everything over the field with two elements, just to get the idea. There is, a candidate vector here, which might be, let's say it's not in the obvious left kernel, and I would like to show that this equation, it doesn't satisfy this equation. There is only a finite list of such vectors, so I may believe that if I do my calculation with probability and so on cleverly enough, I may be able to prove that no such vector exists. But let's think for a moment how should we think about such a vector? Since it's indexed by pairs, I can equate, and it's convenient, such a vector with a graph. It's the indicator vector of the edge set of some graph. So from this perspective, these guys are trivial. And the question is there anything else that would still satisfy this equality? But there is another nice observation, which is that if let's say this is, so the trivial vectors are the graphs or the vectors that correspond to these graphs. It's obvious that if this holds, if I add here something like, let's call it A sub S. If I add here a vector like this, then obviously this doesn't change because A times S, A sub S times this matrix is 0. So all of this really doesn't matter. So this holds, so XA is 0 if and only if X plus AS times A is 0. So there is all equivalence class, X plus every vector like this, they all behave the same way. So in this case, I start, to begin with, I have 2 to the n choose 2 vectors that I have to worry about that might satisfy this. Okay, I've cut the number down a little bit because if any one of them satisfies this, then all of them satisfies this. It's enough that I consider only one vector from this collection. So by doing this, if I give an arbitrary x, so from this equivalence class, which vector should I pick? So without loss of generality, x has the property, x is a vector, and at the same time it's an indicator vector of a graph. So I can think of it, and I will, from these two perspectives. It's a vector and it's a graph. X is thin. Thin means if there is a sum cut. So think of it now, you have to keep these two pictures in mind. It's a vector, but it's also a graph. And let's say that there is some partitioning of the vertices in which X has lots of edges running in this cut, more than half the edges. Then let's say this happens to be S and S complement. If I do this, then I've complemented this set, and now it became a minority. So thin means, i.e., it's a minority in every cut. So the condition that I'm interested in, no non-trivial left vectors in the left kernel.
You allow equality.
Equality, minority including equality. So A has no non-trivial vectors in the left kernel, or A has non-trivial vectors in the left kernel, if and only if it has thin such vectors. So it's enough. From now on, I only consider x's which correspond to thin graphs. And now I take a thin graph. That's the graph. And I ask, what columns can be here and what columns are not to be here if this is supposed to be, if this graph or this vector is supposed to be in the left kernel of this matrix. So if it so happens that I picked up, let's say, this face, then it's not going to be in the left kernel. Why? Because when I multiply this vector by the column that corresponds to this face, I get 1. The inner product of this with this is 1. Or if there is a triangle here, and I somehow picked this column with this face, then again it's not going to be 0. So in other words, let me define. So for a graph G, and think now of a graph G as in the vector, it's all one and the same thing. So if G is a graph with vertex set 1 to n, then B of G is a collection of faces. It's all faces, 2 faces, on vertex set this that have an odd here means only 1 or 3 intersection with the graph G. So X or G is in the left kernel of A if and only if none of the faces in B of G is selected. So make sure that that's a simple but critical point. Make sure that you understand this. If you have if I need to elaborate on this, please ask me. Okay, so these are the columns. Initially B with Shulam and I, when we worked on this, was for bed. These are the enemies of G. If any of those is selected, then G is out. It's not going to be in the left kernel. And, if you want to defeat someone, then the good thing is to have it have lots of enemies. If there are lots of columns, that I still don't know the matrix. It's about to be generated by this random selection. So it's very likely not to allow G be in the left kernel if such columns are many. So it stands to reason I will not do the calculation here. Irit, you still want where is she? You still want the door closed? No, it's okay. Only I exert heat. No, it's fine. You guys are sitting. It's perhaps. Okay, good. So you can understand that a good step in proving such a theorem. So for the proof, we want a statement of the form: if G is thin, then B of G is big. That would help us. It has lots of enemies and they will defeat it. How large can this be? You see, in order to have an odd intersection with G, it must intersect at least one face. So obviously, B of G, always, thin or not, thin or fat or whatever, is clearly less than n times the number of edges, because I have to pick an edge and pick at least a third vertex in order to create a face with it. So that's always true. And a lemma, that a key lemma in our paper, is that if G is thin, then B of G is fairly close to the maximum, is at least a third times. And I thought initially I would show you the proof of this. It's really not difficult. So if you don't insist, this may be a little subtle to do the exact thing, but I think many people here should be able to do this, with not much effort if I replace the third by a 6 or something like this. So think about it. It's a good exercise if you want to think about it a little more. So I will not say much more about how this proof works, but rather I want to switch back and return to Erdős and Renyi and tell you about another phase in this research, which, well, I can't even say ended, but at least, please.
You have to be able to count how many thin graphs there are?
That's right, that's right. Then there is some combinatorics to do, not very different, some counting, and this is essentially the
And when you count
these are the two main
when you
ingredients.
count the thin graphs, will it work if you have instead of 1/3, 1/100?
Yes, actually in my paper with Meshulam, we goofed. We missed this thing that I just told you is so easy, and we proved it with 1/120 over 2 pages. And then later I think Roy presented it at Microsoft, and Latsi Lovas told him, but why this complicated?
Clever guy.
He is a clever guy, yeah, no question. Yes. So this is what Meshulam and I did, and then Meshulam and Wallach modified the proof to work over any finite ring of a billion ring of coefficients. Okay. For Z, we still don't know the answer. Okay. So now I want to switch gears and speak about another result in Erdős and Renyi, which is perhaps the most dramatic theorem in their paper, which is, so back to Erdős and Renyi, perhaps I should, to get the sense. And by the way, if you somehow got lost in thoughts, we all do this the whole time, you can catch up again. So it's going to be quite disconnected from much of what I've done. So Erdős and Renyi proved the following beautiful and very dramatic result. Which I'll give in a title, a phase transition in Gnp at p equals 1/n. So let me tell you what the result is in simpler terms. I spoke so far Gnp and our model XDNP, but you can also think of sequential models like this, and this is what Erdős and Renyi called the evolution of random graphs. You can start with n vertices and just randomly at each step throw in an additional edge at random. And you can ask yourself, what does the structure, what is the structure, what is the typical structure of such graphs? And the answer is this. So as long as P is less than 1 minus epsilon over n, all connected components. So you can think about this in terms of P or in terms of the process. This means about 1 minus epsilon times a half n steps if you count time. So all connected components are small, order log n, and simple. Simple means a tree, or they're going to be a constant number of 3 plus an edge, unicyclic. So the structure is very clear, very uniform, and we understand this. Then at p equals 1 over n, or if you want time, about a half n, over a very short period of time, over n to the 2/3 steps, if you count steps, a really dramatic change happens in the scene, and a giant component emerges. So I'm jumping a little ahead of myself, but at p equals 1 over epsilon over n, there exists a giant, so size omega n component. And this has been studied. This is really very well understood, and this has led to tons of papers and beautiful mathematics and whatnot. In addition, there is something, an additional thing that happens there. Also, at p bigger than 1 over n, the graph, for the first time, almost surely acquires a cycle. Previous to that, as I said, these things are Poisson distributed, so with positive probability they don't exist. So up to this point there is positive probability, no, not 1, but it's a probability bounded away from 0 and 1, that the graph is a forest. And there are various things here. So the question is, so this is really a wonderful result, and you can even see on the net simulations of this process showing this. This is all very nice and beautiful. Is there other higher dimensional analogs? What do they look like? And so on and so forth. Some things are quite, I mean, at least we have the terminology. We know where to start. We know how to translate these questions into the language that we speak in higher dimensional simplicial complexes. For example, we know very well what a cycle is. I'll tell you in a minute. But before I do this, something which is completely mysterious to begin with and took us quite some time to understand is, what is the analog of this? When you go higher in dimension, there is really no natural notion of a component. And as I'll tell you, we finally found a way to state the appropriate, to make the appropriate statement. So, okay, so let me for a moment take a little detour. And one of the main things, one of the main lessons that you can take from that I can take from these investigations and what we learned from this is that really the great importance of not rushing with the questions and thinking deeply about, you know, what are the good questions. It's really something that perhaps too few people are doing. So I advocate this very strongly. You know, what do you want to prove? And so here when you start, it can be quite confusing, because let me remind you about the following very easy theorem that appears in every basic course in discrete math. The following are equivalent for an n-vertex graph. So n-vertex graph with n-1 edges. G. 1, G is connected. 2, G is acyclic. 3, G is collapsible. Perhaps you don't know what that is, but I will explain momentarily. And 4, so these two parts are a little unfair. These two parts appear everywhere. These perhaps a little less, but I want to elaborate on this a bit more. let's leave 4 open for the moment. I'll come back to this in a minute. So, and of course, this is what we call a tree. So what is collapsible? And it's really a very easy exercise to see the equivalence also with this. So what is an elementary collapse? If in a graph you have a vertex of degree 1, then elementary collapse means that I throw away this vertex and this edge. And collapsible means that I can keep doing this and eventually eliminate all the edges. That's collapsible. And it's really a very easy fact that, now the point is that in general dimension, this is no longer true. So in general D, these two things are equivalent. I'll show you in a second. I mean, I have to make the right definitions. This implication is correct, but this implication is no longer true. And now let me also fill in this condition 4. So what is condition 4? Let's again return to our friend, the incidence matrix, so it's the boundary operator. How can you read from a matrix like this? So that's a graph. It has n vertices, and let's say this has n-1 edges. Ron, I'm sure you bet yourself that I'm not going to answer the previous question, but the moment came. I'm going to answer it. What's the rank? Okay, it was worth the wait. What's the rank of this matrix? It's n-1. There is exactly one linear dependency, which is that the rows sum to 0. So an equivalent statement. So now think of the edge set or the column set as the same thing. That's equivalent to the fact that the column set in A form a basis to everything if I took to this. So being they span the column set of this matrix. And so now this is just linear algebra, very simple linear algebra. So I have to explain to you now connected. In fact, we know now, we know how to think about it. We just discussed it at great length. So I have to tell you what a cyclicity is, what collapsibility is, and so on and so forth. So the first order of things is to tell you what the analog of this is. And I'll do it again just in 2 dimensions. And it's something very, very similar. So what is a collapse? If you have an edge that is covered by a unique face, then the elementary collapse means I throw this away and I throw this away. Okay? And as Tal explained to me many times, those of you who have some background in topology, or I heard it from Gil, who's sitting there, you can show Gil as well, as I did with before, I don't know. You stick your finger. This is a homotopy equivalence. You stick your finger like this, and you kill the edge and the face. And the complex from a topological perspective doesn't really change. But I would like to give you my take of it, the most elementary one. Let's think about it for a moment. When we talk about cycles and so on, and we already saw this, we're interested in linear dependencies among the columns of these matrices. And so previously we saw that an isolated vertex means a row of zeros. What does this look like? What does this look like? This looks like a row in which there is a single non-zero. Everything else is 0. So if you're interested, if you're asking yourselves about linear dependencies among the columns of this matrix, which we will in a second, then obviously this column cannot participate. Because if you take this with any non-zero coefficient, there is nothing else to zero it out. So you might as well throw this column and this row, which is exactly what we do here. Okay, so there's also a linear algebra way of thinking about collapsibility. And in fact, if you just think about it this way, you'll see very quickly why this implication goes. But let me, if you never saw this, so we already had the Fano plane. Here is another wunderkind of combinatorics that everyone should know, which is this guy. This is the 6-point triangulation of the projective plane. It has, you wouldn't be surprised, 6 vertices. These 6 vertices, so these two are identified, it's the same vertex, and these faces, as in this picture. And so I'm still paying my dues here. When you go higher in dimension, the rank of the matrix, this follows easily. It's from this, the rank here is going to be n minus 1 choose 2, and in general, that's the rank of this matrix. So let's do the calculation. N minus 1 choose 2, n is 6, so it's 5 choose 2, so it's 10. And if you count, there are really 10 faces here. So in terms of numbers, this is correct. Of course, this is not collapsible, because every edge here is covered twice. You can't even start collapsing. And at least if you do this over the reals or over the Q, there is no cycle here. So in fact, I'm jumping a little bit ahead of myself, and I should tell what a cycle is. So how do we interpret cycles using adjacency matrices and so on and so forth? A cycle in a graph is just a same thing as a non-zero vector in the right kernel. It's just a linear dependency. It's a collection. Let's do it again over F2. It's the simplest. Then it's just zeros and ones. It's a collection of edges where every vertex has an even degree. A cycle, or it's exactly the cycle space. So we're now able to look at these things to formulate analogs of Erdős and Regnier's results, and at least ask ourselves, but the questions, and see what we can say about answers. But here, and especially after I showed you this example, it's clear that now, and that's quite common, the picture is becoming more complicated. So whereas Erdős and Regnier could ask, what is the critical P for almost surely a cycle? And they said in graphs. And they told us that the answer is 1 over n. Here we have at least 2 separate questions. A priori, we don't know, they might coincide. But we can ask a question, what is the critical P for collapsibility? And I have to apologize that I'm a little doing an abuse of language, so I should really be calling this D minus 1 collapsibility. So when is a 2-dimensional simplicial complex 2 collapsible, or 1 collapsible? I can eliminate, doing these steps, all the 2 faces. Okay? So that's one thing. And what is we can ask, what is the critical P for almost surely there exists a right kernel, or the right kernel, almost surely the right kernel is non-empty, non-zero. So just because of these implications, it's clear to begin with that there is such an inequality. But as I will tell you in a minute, it's actually like this. So there are 2 separate separate thresholds here. Okay, and we still haven't spoken at all about how to capture the concept of a giant component. Okay, so now let me try and tell you what the results are, and try to give you again a little taste of 1 or 2 ideas from the proof. Okay. So, you know, we're becoming weaker degeneration. So what for the Erdős and Renyi was part of a paper was for us 4 separate papers. So this combines, this theorem combines 4 papers. My co-authors are Lior Aronstam, Goyi Meshulam. I always make the same mistake. Somehow I stuck it into my head that Wuchak, this is a W, but actually explained to me that this is an L. So my apologies, Thomas Wuchak. And Yuval Peled.
They have these papers of Wuchak and Luchak.
Right. Apparently it's a very common Polish name. This is what I learned. So the theorem says that the critical P for collapsibility is, we have, I'm not giving you, there are explicit formulas, implicit formulas that you can calculate on the computer in any accuracy that you want, log D over N. Actually, this is in the language of topology where HD becomes non-zero. P for HD non-zero is D plus 1 minus Littler of 1 divided by N. So you see these two thresholds are quite different.
But you have to say over which group.
Okay, this is completely combinatorial. Here there is no dependency. Here there is no dependency on anything. It's completely, collapsibility is a purely combinatorial condition. Here, the upper bound is for every field, and the lower bound, that's the last piece in these 4 papers with Yuval Peled. Lower bound, we only know, let's say, over the rationals or over the reals, and we definitely, although Yuval told me that he has some new ideas. Yuval, can you? No, too much, huh? It worked so well the first time. You should have sat in the front row. We could have done the same trick again. Anyway, we don't know. We certainly don't know how to do this over, let's say, finite fields or finite characteristics. The proof is very much analytic and okay. So these are theorems. What? Thank you. There's a, I read it first time in a book of Hasidic tales, but it's also told in all sorts of political contexts about this great rabbi who travels between the villages, and in each place he comes and preaches, and everyone admires him, but of course he doesn't drive, he goes with a carriage, and he has a carriage driver who's a simple guy, and one day he says, Rabbi, you are having all the time of your life. They're all, crazy about what you're telling them, and they want to hear you and listen to you. Why don't we switch roles once? And the Rabbi says, why not? And now he drives, and the driver, the carriage driver sits in the back. They come to a village. The guys don't know him, so he plays the great rabbi, and they eat and everywhere. And then, after dinner, they want to ask him all sorts of complicated halachic questions, Jewish law. These things are complicated like you wouldn't believe. They ask him something very complicated, and the guy goes, this is so simple. Even my driver can answer this, please. So even our photographer can ask good questions. Okay, good. Okay, so actually, Gil is right. I neglected to mention something here, which is so. Actually, while we're at it, I'll take the opportunity and tell you a little bit more about this, which is really interesting. So let me speak about this. We have also done a lot of computer experiments, and this is more or less more or less like the rabbi and the driver, which means we do computer experiments by me telling Yuval, why don't you test this on the computer? And then he comes back an hour later with some amazing results. So there are wonderful computational things that we know here that we still can't prove. But let's think about this again sequentially. So you start, let's say, again, let's do it. These are all the pairs, and you start picking columns at random, triples. And you ask, when is the first, as opposed to what we had before, now initially there are, of course, no linear dependencies among the columns. That's a cycle. And you're asking for the first moment that a cycle occurs. Now, these questions have been asked in graphs. You can do the same thing in graphs. You start, as we described before, start with n vertices, start throwing it, and you ask about the first cycle that is generated, how this is distributed. We understand this very well. Here, there is something, and the distribution has a full support. Everything essentially can happen as the first cycle. Here, the picture is very different, and that's already one good example for how the stories really diverge. Here, the first occurring cycle, 2 hours, right? Any English speaker? 2 hours? No. 1? Thank you. The first occurring cycle is either, there is a trivial one, which is take all the 4 faces of a tetrahedron. That's a cycle. But the number of such things is Poisson distributed. So they happen with probability that is bounded away from 0 and 1. But if this doesn't happen, then the first cycle is really huge. It has quadratic number of faces in it. Okay, so this is a more precise, and thank you, Gil, for pointing out this. So what I don't have that much time, so what I'd like to explain to you is at least one idea.
So it's a sharp threshold. I like the case of graphs.
Yes, okay, yeah. Okay, very good. So I want to start. So this is even years before I knew that Yuval Peled existed. I had an undergraduate student who did a project with me. So I'm now picking up on Noga's question. And these are graphs that I used to look at, and amaze myself and not being able to make any sense out of them. But finally, in this last paper with Yuval, we understand the picture. So there was this guy, he did an honors undergraduate project, Gavri Smith, and just a smart guy. And then just to make sure that I can trust his simulations, I told him just to run on the computer where I knew the answer, the Erdős-Renyi process, the evolution of random graphs. And what exactly did I tell him to do? You start with a matrix and n by something, and you pick each time a new column. When you add a column, either the rank of the matrix stays put or goes up by 1. And I told him, do a graph which shows you at each step what is you repeat this now many times. So you fix some large number, n, 100, let's say, several hundreds, and repeat this process many times. And tell me, in step number 107, how often did it happen that the rank went up? And so he came back with a very nice graph like this. And by now, you know pretty much everything that is to be known about this. This ends at about corresponding to p equals log n over n, part 1. And this happens at about p equals 1 over n. Very nice. So at this point, I knew I could trust Gavri. And now I told him to do the analogous thing in 2 dimensions. N choose 2. By triples, and now you add triples. And then he came back with the following amazing graph. It's really a cliff. So at least if you speak physics, it should be very clear to you that this is a second order phase transition. So the function is continuous in the limit, but has a non-continuous derivative. And here even the function is discontinuous. There is a jump. And for a very long time, I knew this and I wasn't able to prove anything. And so the question was, how do you capture this concept of a giant component? This is the emergence of the other Shreni giant component. That's the emergence of the giant component in 2 dimensions, but in general in every dimension. And by the way, every physicist to whom you tell that, you saw such a phase transition in dimension 1 and such a phase transition in higher dimension would say, of course, but we knew this the whole time. So how do you capture this? The point is that there is really no natural notion, as I said before, of a connected component. And the key idea that really got the whole thing going is this notion of a shadow. So let's say this first in graphs. You have a graph. It has several connected components. And now take an edge that is not in the graph yet, that you want to add. I say that the graph can be in the sun if it connects two different connected components. It can be in the shade if it connects shade or the shadow. So the shadow of this graph are all the edges that are not in the graph and connect two vertices which are in the same component. And one thing to observe is, you have to look a little bit into the details of the other Schrödinger description of the emergence of the giant component. So in GNP, the giant component emerges simultaneously with the emergence what?
Of shade.
Exactly, of giant shade. Of giant shade. Giant means omega of n squared shade. One part is really easy, and it's really not difficult at all. If you don't need to do anything deep. You just have to look a little bit, be careful with the details. But of course, when the giant component emerges in the GNP model, all the components but this one are tiny. And so and this is still very sparse. So a constant fraction of the edges outside of the graph that you've created so far are like this. They're in the shade. So they're even in the shade of the giant component. So these two things are concurrent. And this is, the point is that the notion of a shadow you can define also in general dimensions. So the same thing. So what is the notion of a shade? You do. I'll again speak in 2 dimensions just because it really is good enough for our purposes. You have some 2-dimensional complex. These are, and again we're looking at this. It's essentially not so far from the experiment that I described, the numerical experiment. These are the two-dimensional faces of the complex. And what's in the shade? What's in the shade is any new column that you can add that is linearly dependent on those. And so this is what we take as our definition of the emergence of a giant component. Rather, we're looking at the emergence of a giant shade. And that now we can prove everything happens at the same point. So that happens precisely at the threshold for the emergence of the non-vanishing of the Deth homology or the occurrence of a cycle. And we now have a fairly nice and clear picture of everything that's happening there. Let me only say one more thing.
So giant is n cube.
N to the D. N to the D in general. And that happens in a first-order phase transition, discontinuous in the limit. And just the fact that right, you're right. And just the fact that the collapsibility is really less than then this leaves here many. So I initially intended to tell you a little bit about this, but I think you've suffered enough for one day. I'm sure I already know some examples, but there are many fascinating objects in here which in principle topologists knew about them, but one nice thing that these theorems tell you is a huge supply of random simplicial complexes which are not collapsible and yet are acyclic. And I'm sure their properties will be very useful for all sorts of things that we want to study in the future, but I think it's also a good point for me to stop. So thank you.
So we still may have time. I mean, I'm so fascinated by this camera that I try to see. So what exactly should I do to see? Okay. So,
Look at
so
Gil.
we still have time maybe for a short question or two. I'm not sure.
Yes,
Ehud wants to ask. Noga, Ehud wants to ask. Aaron wants to ask.
Yeah,
Yeah.
but one.
Sure.
Is it also interesting to consider the case that T goes to infinity?
Presumably yes, but I don't know anything about this.
So when all the results you wrote there
Are constant D. Yeah. I suppose yes, but I don't know any. So this asymptotic, I mean, there is a double asymptotic. So when I write log D over n, this little o is dependent on D. I can very well imagine that yes, but I don't have any concrete question that I know. That I have tons of questions, but nothing with respect to growing D. Ehud, please.
So can you explain why it's the first order phase transition and not the second?
I'm
Or
not.
can you only prove it?
Do you have? I don't think. I mean, the proof is very. Do you have an intuition for this? No, I don't think that at the moment we can provide. I'm unable to. It's a good question. Perhaps it's a good thing to. No, right here and now I don't have any simple explanation. The proof is fairly complicated. It is using this. That's another thing which I was hoping to mention, but I don't have time to. This key theme, and in hindsight, we did it. So it's really, we had 4 papers on this, and we used it 4 times, but only in the 4th step did I realize that this is what we were doing the whole time. This weak local limits. That's a key theme in the whole thing, which is most pronounced in this last paper with Yuval on. But that's really. I found out now how really profound and interesting this concept is. So that's a major lesson that I learned. So it's very analytic. It draws on ideas that have emerged in that area. I don't know that I'm able to give you really a simple explanation why it would be a first order phase transition.
Is there a concept for projecting high-dimensional simplex into one-dimensional?
It's very combinatorial. The whole thing is very combinatorial. So there is really, we are not looking at all at geometric realizations. You can take so it's very combinatorial. So not that I it's worth thinking about. It never occurred to me. But you have גיל משחק, pinecone perhaps, Gil, on the head. No, I don't have much to say about this, sorry.
So someone else wants to try to appear on the screen?
Only in shadow.
Okay, so I remind you that now we have a reception downstairs, and let's thank Nati again.